Hello students, welcome to the course Verilog HDL. In the previous video, we started with gate level modeling examples. Okay, the first example we seen was a gate level 4:1 multiplexer. So, and also we have seen the procedure. Okay, if any design is given, so how you write a complete Verilog description, stimulus and simulation output. Okay, so today we will see another example. So it is a 4-bit ripple carry full ladder. Okay, so it is an adder circuit. So it is an adder circuit. Okay, that means you have to do a Boolean addition, and it is a full adder circuit. So it is complete addition it will do. Okay, and it is a ripple carry. That means so it will be constructed from a 1-bit full adder. The carry out of the 1-bit full adder is given to the carry in of the next full adder. So like that we have 4 full adders. Okay, so that's why it is called as 4-bit ripple carry full adder. Okay, so we'll try to understand this design, and just we'll recall the procedure for carrying out this. Okay, same way, first you need to have the IO diagram or logic symbol, so truth table, then logic expression or Boolean expression, and then logic diagram. So once you know the logic diagram, we will write the Verilog description. It is an one-to-one correspondence using the gate primitives. We will build the gate level construction. Okay, so then you will write the test bench, or you will give the inputs to the design, so that you will verify the output. Okay, so design is correct or not. So by this way, so we are going to correct both the syntax errors and semantic errors. Clear? So in 4-bit ripple carry full adder, we design a 4-bit full adder, okay, whose IO diagram is shown here, and also we use primitive logic gates as we have seen in previous case, and or and not gates, and we apply stimulus to the 4-bit full adder to check the functionality. Okay, so for the sake of simplicity, we will implement a ripple carry adder. So there is look ahead adder also is there. We'll see that in data flow description. So here we'll focus on ripple carry adder. The basic building block is a 1-bit full adder. Okay, so that's why before we build the 4-bit ripple carry adder, so what I do is we'll construct first 1-bit full adder, symbol, truth table, Boolean expression, and logic diagram and Verilog description. Up to that I will write for 1-bit full adder, and then in 4-bit full adder I will just call the instance 1-bit full adder. I will call 4 times with its inputs and output, so it will complete the 4-bit full adder. Okay, so this is the IO diagram which we have seen in the list of ports discussion also. So you will be having 3 inputs, A, B, C in, sum and C out. So this logic symbol holds good for both the 4-bit triple carry full adder as well as a single 1-bit full adder, because if you have A of 4 bits and B of 4 bits and the sum of 4 bits, then it is a 4-bit full adder. Okay, C in and C out are scalar inputs. Okay, so if you does not have vectors, so just you have 1-bit scalar, so then it becomes the 1-bit full adder circuit. Okay, so nothing but what we are going to do is, so if you have an example, so 1101, okay, 1001, I have something like this 4-bit inputs. I need to do the addition. Okay, so this is the adder circuit. So here the first bit will be A, okay, the second bit will be B, and the carry computed from each bit addition is called as C in. Okay, so very first addition you don't have the C in, it will be 0. Okay, so 1 plus 1, it is 0 with carry 1, okay, plus 0, so it will be answer is 0, and you will get a carry 1. Okay, so like that we will perform the addition. Okay, so this new value which is came out, which we call it as the sum. Okay, some cases S we denote, and at all the addition, after doing all the addition here, okay, so finally we will get a one more carry bit. So this carry bit we call it as the C out bit. Okay, so this is the 4-bit addition. So to perform such 4-bit addition, okay, so we'll use, we are designing a circuit now. Okay, so hope you are understanding. So if you know this 4-bit full adder, you can do it for, extend it for any number of bits, n number of bits also you can do, but for all these full adder. So 1 bit full adder is the basic here, because first we'll try to do this much only this much. Okay, so we'll have a 1 bit, b 1 bit, c in. Okay, and then sum and c out. Each cases you will have the c out, right? So this will do. And when we are doing 4 bit triple carry adder, so this carry out will be given to the scene of the next full adder, that we'll see next. Okay, so hope you are understanding what we are going to do here. So now we'll see the truth table of full adder. Okay, so just follow the same notation throughout the program. Okay, so I'm using small a small b, c underscore in, sum and c out. Okay, in between there may be mistakes in notation, so you follow the common one throughout the program. Okay, till the end of the program. So this is the 1 bit full adder truth table. So okay, so you have already gone through. So the names may be changed. Okay, capital A written, so you correct it. Okay, so a b c underscore in, whatever I have given, the same thing you note down. Sum was same, so carry sometimes we'll write. So in my example I will take it as c out. Okay, so like that you make the correction. So now 3 inputs are there, you have to write the 2 to the power 3 8 combinations. Okay, so that means 0 1 up to decimal 7. So its corresponding binary equivalent are 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 and 1 1 1. So now once you know the, so from the IO diagram you come to know 3 inputs are there. So for 3 inputs how to write the sequence you come to know. Now you have to do the addition operation. Okay, so 0 0 0, if you do the addition, so you'll get a sum 0 and there is no carry generated. Okay, so then if you do 0 0 1, okay, so it will be done as 1 bit full adder. So 0 0 will be added, then carry will be added. After this result 1 will be added, so you'll get a sum 1 and there is no carry. 0 1 0 also you will get a sum 1, no carry. So whereas in the case of 0 1 1, so what will happen? So it is a Boolean addition, so you will have a sum 0 and carry 1 will be coming out. Okay, so that is the C out. Next 1 0 0 combination, again you have 1 sum and 0 is the carry. So next all cases you have more than ones, so that's why you will have sum is 0 here, carry 1. Similarly 1 1 0 you will also get sum 0, carry 1, and 1 1 1 3 inputs are there. So how we do addition here? First we'll do 1 plus 1. Okay, so here you will get sum 0 and carry 1, and then one more 1 is there. So that's why 0 plus 1 is 1 and this 1 will be followed here. That's why you are getting sum is 1, carry is also 1. Okay, so hope you have understood the truth table. So now you can write the kmap for this sum and c out. Okay, so you will get a simplified Boolean expression, or another way also you can write for sum. So wherever 1 is there now, okay, so group those product terms and just add it, and then using the De Morgan's theorem and the Boolean laws, so you can simplify the things. Okay, so that we will do in the next, that is the Boolean expression part. Similar way carry also, wherever 1 is there, so you can group it as we have done in multiplexer. Okay, for example 1 I will show you for this. So here 0 means a bar, 1 means b, 0 means c in bar, like that. Okay, like that 4 terms you will get, then you can simplify, you will get an expression. Okay, that also you can do, or else kmap you can do it. Okay, so kmap part you have to do, I have not shown that directly, I have simplified expression I have written. Maybe in the lab part I may show you. Okay, so this is the mathematical equation I will get, okay, for the full adder. Okay, so there are different simplification output will get. So for sum, if you do in both way, I shown you first, if you group 1 terms and if you simplify that, and also if you apply the kmap, right? So you know the kmap one I will show you. Okay, so that similarly you can do that, right? Anyhow you can write. So this side I have 1 input, this side I will have b and c in. Okay, so 2 inputs I will keep. So here 0 and 1. Next we'll have 0 0 0 1 and 1 0 will be at the end, right? So this is why you know. Okay, and then 1 1. Okay, so why this is because 0 0 0 to this only 1 bit is changed here. So 1 is already there, so this 0 is changed to 1 now. Next 1 1 is there, so just 1 bit is changed. Every time 1 bit transition. Okay, so now if you enter the output there, 0 0 0, you had some 0, 0 0 1 1, 0 1 1 0, you had 0 1 0 1, next 1 0 0 1, 1 0 1 0, 1 1 1 1. Okay, so in this case, even if you make the KMF also, you'll get the same, right? So all single bit, there is no grouping here. Okay, so you have to write all the terms wherever one is there, and you have to simplify using the Boolean laws algebra. Okay, so you'll get A XOR B XOR C. So I didn't get the proper symbol in my text, so I have used this. So it is a XOR symbol. Okay, A XOR B XOR C, that is the sum expression you will get. Similar way, if you do the carry now, you will get two types of output. Okay, so don't confuse with this. Normally in lab programs and all, I may use the second one. Okay, so this one I may use. Okay, so here in this text they have used this. So how you got this? This is from K-map simplification. Okay, so again I won't write everything. So 0 1, okay, 0 0, so you know that 0 0 0 1 1 1, and here 1 0. Okay, so just enter now. So 0 0 0 0 0 0 1 0 0 1 1, you have 1 0 1 0 0, carry out. Okay, 1 0 0 0 1 0 1 1 1 1 1 1 1 1 0 1. So because of this, you will have a three combinations here. Okay, so this is one group, and then this is one group, and then this is one group, right? So three min terms you will get. So when you add that, so actually you are getting this A into B, B into C in, A in into B in. Okay, so A, B, B, C, and C, A. So just you can verify. Okay, so but here in this example, they have went through this method. Okay, so just wherever one is there, grouped it, and they have clubbed it. So when they got, so they will get this answer A into B. You can get this. Okay, so you try out, and then A XOR B. Okay, so this is like using two half adders output you will get. Full adder can be constructed using two half adders and an OR gate also you have studied, right? So that output it is coming here. Okay, so that we are using. So this is the output with respect to your. Okay, so same notations you use, whatever we have used, sum C out. Okay, so this carry additional I have shown you because this also you will get. Okay, but I am not using this in this example. Hope it is clear. Okay, so now we'll use these two expressions, sum and C out first. Okay, not the this one, and we'll draw the logic circuit. Okay, so how it looks like, see here, A B. So there are some mistakes also there, just very careful. So first one, you have A XOR B. So I directly am not using 3 input XOR gate here. Okay, because A XOR B I have in this C in C out also. That's why I have taken like this. So it is a half adder actually. So one AND gate and one XOR gate is a half adder circuit. So I have added two half adders and one OR gate. Okay, so here also mistakes are there, I will tell you. So this is an A XOR B now. Okay, that is stored in S1 signal. Okay, as we have used in multiplexers also. And this is A and B, that will be carry of the this one. So A dot B, this is the C1 output. So then for next XOR gate, I have used A XOR B and then C in. That means what you will get, A XOR B XOR C. That is what the expression for sum. Okay, so like this we have constructed the logic gate. Okay, then this is A XOR B and then you have C in, right? So that is the second part you had in the C out, right? This is A XOR B dot C in, that is the S2 output. Okay, so now this term and this term we are going to add it in this OR gate. Okay, so this is not XOR gate, so they remove this part. Okay, so just it is an OR gate. Okay, so this is AND gate lower one and this is an XOR gate. Okay, so this is why I am writing this here, because you should know which primitive to use in Verilog description. Okay, so OR gate, it is not XOR gate. Okay, so finally you'll get the C out when you add this. Okay, that is what the Boolean expression you had. So that's why. So if you are using this type of XOR and AND gate formation, you will get this expression, Boolean expression. Okay. So that's why. So if you use the K-map for both, so you will get this sum will not change in both cases. This will be same. Whereas there we will have three to input AND gates. That design also will see in exercises and also in lab part. Okay. Fine. So hope it is clear. So now you know from yesterday, right? So how to write the Verilog description now. So understanding this much here, it is very important. So now you have the IO diagram. So you have ABC in, sum C out. So then ABC in are the inputs, sum and C out are the outputs. Then wire you have to use for S1, C1 and S2. Then you have to call the one first XOR and AND gate we are calling. First XOR gate S1 is the output, A and B is the input. Next AND gate I am calling. So C1 is the output, A and B are the inputs. Next I am calling sum. Sorry, XOR gate again. Sum is the output. S1 and Cin are the inputs. Next AND gate I am calling. So S1 and Cin is the input. Then finally OR gate I am calling. Cout is the output. S2 and C1 are the inputs. Hope it is clear. So if you have understood, straight away write the program and then you can pause the video, complete it, and then you can verify, so that you will improve your confidence in this way. Okay. The logic diagram for the 1-bit full adder is converted to a Verilog description shown in example below. Okay, so I have given the name. So this name you careful, because this name only I am calling in 4-bit full adder. Okay, so this is I am user defined name now. Okay, so this is a user defined construction now. So I have given full adder name. You can give any name. Okay, module name full adder. Then all the list of ports, sum, Cout, ABC, anything you can write. Okay, any order you can write, but all should be there inside this. Okay. Then output are sum and Cout, all are 1 bit. Input is AB, Cin. Then internal nets wire S1, C1, C2. Okay. So you can pause the video and write down. Okay. Or verify what if you have written already. I will go further. So then I just need to call the instances. Okay. Git instantiation I need to call. So first I told you XOR. S1 is the output, AB is the input. Next AND gate, C1 is the output, AB is the input. Second XOR gate, sum is the output, S1 and Cin is the input. AND gate, so C2 is the output, S1 and Cin is the input. So here XOR they have used, so strike out this. Okay, not required. OR gate it is. Okay, just write OR, Cout, C2 and C1. Okay, so this is the program, and finally end module. So we are not writing now only the stimulus module, because this is 1-bit full adder. So once you know this, now we first build the block diagram of a 4-bit full adder now. Okay, so 4 times I need. So ripple carry I told you, 4-bit ripple carry full adder. So what is meant by ripple carry full adder? Its block diagram we will see, and then just we'll call this full add program 4 times. Okay, so just we'll see that part in the next. Okay, and then after that together we'll write for stimulus video. Okay, for 4-bit full adder only I am calling the instance. Okay, so a 4-bit full ripple carry full adder can be constructed from 4 1-bit full adders as shown in figure below. Okay, so figure is shown here. So note that here FA0, FA1, FA2, FA3 are instances of the module full add. So that's why I have written 1-bit full adder first with the name full add. Okay, so now just see the, so I just shown you in the very beginning, right? So I have 4-bit, right? Something like 1101 1001. Okay, so I'm adding these bits. Okay, so I'm starting from this. So some books they will use from right to left. Okay, because as it is in this, okay, how we are doing addition normally, that's why they will start from C in here and C out this time. Both are correct. So in this my example I have taken left side. Okay, so first full adder I have given the instance name FA0. Inputs are, it is a vectors we are using now 4-bit, right? So first one we will have A of 0 and B of 0. So Cin will be not there, so it will be initiated as 0 or else kept it as it is. Okay, so output of this is sum 0, and the carry produced from this full adder is given to the Cin, right? Cin as C1 we are giving. So the intermediate signals we are giving names here. Okay, so this is nothing but 1 1 here is A of 0, B of 0. So Cin is nothing is there, so it will be 0. So what is the output you are getting here? 0 and carry 1. That means sum is 0 here and carry is 1. So next case 0 0 1. That means what? This is 0 0. Okay, A of 1 B of 1. So one previous carry added. So you'll get a sum 1 now. Okay, so no carry. So that means here 0. C2 is 0. Next A2 B2. Next what you have 1 0 combination, right? So it is A of 2 B of 2. 1 0 and 0. So you'll have sum 1 and carry is 0. From the truth table only I'm writing this. Okay, 1 0 0. Okay. So next case what I have 0 carry. So 1 1 bit is there. Okay. So again A of 3 B of 3 1 1 is there. So and carry is 0. So what is the sum you will get? 0 and C out is 1. Okay. So that is what you are getting here. 0 and 1. So 0 1 1 0 is the 4 bit sum and C out is the 1. Okay. So this we need to write the program now. Okay. Hope you have understood. So this structure can be translated to Verilog as shown in example below. So some of the notes, observations from this program I am telling first only. Okay. So note that the port names used in 1-bit full adder and a 4-bit full adder are the same, but they represent different elements. Okay. So we have used ABC in same only we have used. So don't confuse with that. The element sum in a 1-bit adder is a scalar. Okay. Quantity, and the element sum in the 4-bit full adder is a vector quantity. That means it is a 4-bit. That is the difference. Verilog keeps names local to a module. So whatever you are writing inside that module, the names are local. Okay, it is not global. So that's why it is not a problem if you are using the same names. Okay, names are not visible outside the module unless hierarchical name referencing is used. Okay, so why we are mentioning these terms here and there? Because when we are explaining the programs itself, some of the minute concepts of Verilog also try to explain it. That's what the author has done. Okay, so that's why I'm following his same way, because that is the book used throughout for learning Verilog. So what methodology he has used, so that only we should duplicate it. Okay, so okay, so that's why I'm mentioning these things. Okay, so I would have taken some other names and I would have not mentioned these things here. Okay, but this should be kept in your mind. Okay, so Verilog keeps names local to a module. Names are not visible outside the module unless hierarchical name referencing is used. Okay, so where this is used, now you understood. Okay, if you have to make it as uh, visible outside the module, then you will use it. Okay, as in C programs you have local declaration and global declaration, right? If you write int a equal to 10 outside the main program, it is global. If you write inside that, it is local. Okay, also note that instance names must be specified when defined modules are instantiated. Defined modules, here I am defined, right? 1-bit full adder I have defined. That's why I need to give a instantiation name. Okay, but when instantiating Verilog primitives, in 1-bit full adder I have called primitives, right? There I have not given any instance name. So this I am again stressing here, this point. Okay, instance name where we have to give, where we are not, should not give. Okay, so with this we show the program, a very simple 4-bit full adder. So first we'll give a name, module full add 4 we have made. Okay, not same name you should not give. You can make ripple carry also, you can write. Okay, any name whichever convenient to you according to the identifiers formula. First name should be a letter, number should be there, underscore should be there, dollar symbol should not come in the beginning, right? So these some rules if you follow accordingly, you give the name. Then same thing, it will come list of ports, same as 1-bit full adder, but difference is scalar and vector. Okay, when declaring here, so sum you should declare it as vector 3 is to 0 sum. Output is 1-bit scalar, input again 3 is to 0 ab vector, and input Cin is 1-bit scalar. So then we have used here 3 intermediate signals C1, C2, C3 to hold the carry, that should declare as wire. Okay. Next what you have to do, the 1-bit full adder, whichever program we have written first, that we have to call it 4 times. Okay. So full add names also I have mentioned there in the block diagram, right? So FA0, FA2, FA3 like that. So first full adder, if you see, sum 0 was the output and C1 was the C out. And then A of 0, B of 0 and Cin was the input. Similarly, second full adder, sum 1, then C2 was the output, A1, B1, and the carry generated from previous is the Cin, right? Similarly, third full adder, sum 2 is the output, C3 is the carry, Then A of 2, B of 2 are the new input values, and previous carry will be given to this. That's why it is ripple. That means next addition should wait for the previous addition to should happen. Okay, so sequential. Sum 3, then finally we have the C out here, and then A3, B3, and the previous addition carry C3. Simple. Okay, so if you know the 1-bit full adder how to write, okay, so 1-bit full adder is constructed using Verilog gate primitives, and now using that 4-bit full adder I have just, so with this knowledge you can now extend it to 5-bit full adder also, 10-bit full adder also, 20-bit full adder also. Yes, you can do that addition. So just what you have to do, call that many number of 1-bit full adder. Okay, so since here full adder is a user defined, so you need to give the names here. Okay, so this much. Okay, so once you have understood now this design part, so we'll do the stimulus module now. So we have to verify, no, is it working like a full adder or not, as expected answers are coming or not, just we need to check. But since here it is a 4-bit full adder, okay, so you have many combinations you will get, it's like 16 combinations you will get, right? 2 to the power 4, 16. So all you can do it like in multiplexers, but multiplexer you had only 4 combinations, so we have done it. But in 16 combinations not necessary, some random 3 or 4 if you see, so you'll come to know it is working, right? So same way I'm doing here the stimulus module, I'm not writing it for full. Okay, finally, the design must be checked by applying stimulus. Okay, as shown in example below, the module stimulus stimulates the 4-bit full adder by applying a few input combinations, not all. Okay, so just few input combinations, just to show you a stimulus module, and we will monitor the results here. Okay, so previous example, I used the display system task. Okay, so system task you have learned and you have not applied properly, right, in real time. So that is the, this is the platform now we are using that real time. So in this example I am using now monitor, so see the difference to that program and this stimulus program. Okay, there we have called every time display 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 display, now we are not calling like that. Once we will do monitor, so it will take care. Okay, so we'll begin with the stimulus module. So module name stimulus, so stimulus module, no list of ports and port declarations, clear. Then input should be declared as register because they should hold the value. So some, so this AB, okay, so 3 is to 0, everything capital we have used to just to differentiate that, and the same notation we have used. Output should be declared as wire net data types. Okay, so that's why this is used. Okay, so we'll continue. Next we'll just call the design. Okay, so 4-bit full adder we will call, because this 4-bit full adder again will call the 1-bit full adder, right? So that we are not doing one 4-bit full adder, we are calling here, what is its name, full add 4 now. Okay, its name is full add 4, and we have given some new instance name. Okay, so it is just for reference when we are checking. Okay, so it is not doing much things in the design. So its outputs are according to here declaration sum cout abc in. So this is called as connection by ordered list. So there also you have written in same order, right? First sum, then cout, then abc in we have written. Okay, so if you are changing this, so problem will come. Okay, instead you can use the connection by name. Okay, some concept I have mentioned in the fourth unit or third unit. Okay, so just go through that what is I am mentioning here. Okay, then initial, so as you do practical and practice that, if you get errors, so you will understand that. Okay, so next we have to write the monitor statements for that initial begin. So when we are writing monitor, so it should be written a separate initial block, so begin and end, inside that we are writing here. So display not like that. So dollar monitor was the system task, so just space you give, some typing mistake, I have not given the space. No, space is not required. Okay, let it be same. So dollar time simulation time it will invoke, then just whatever inputs are changing, okay, as we are giving, so it will be highlighted here abc in value, just hyphens are given just to differentiate input side and output side. Okay, so then we are displaying cout and then sum. Okay, so cout first, sum we are doing because when we do 1 plus 1 addition, so you should understand 1 0. Okay, so in that same order it should be, that's why that format is used, cout and then sum. Okay, so this is monitor part, this is instantiating part. Now you have to pass some few combinations of input we will use abc in. Okay, some few combinations. Okay, 0 0 0, any few combinations we will use. AB are 4 bits, no? So that's why. So initially we are keeping C in as 0. Initially we keep, so initial again I should write one more initial and begin, and C in I will keep 0, and I will change the few values of A. First I will take A is 0, B is 0. Okay. So as you have this value, so monitor will do the computation now. All are 0 means sum and Cout are 0. This we'll see in next simulation output. Next, I am giving the value decimal 3 and 4. So you know what is 3 and 4. 3 plus 4 is 7 in decimal. Similar way in binary, what is 7? 0, 1, 1, 1. Cout is 0. There is no carry out from this addition, right? Cout is 0. Then A is 2, B is 5. Again 2 plus 5 is 7, same output. Then you have A is 9, B is 9. So 9 plus 9, 18 you are getting. Okay. But how it will be written 18 in binary? So that you have to do by successive division of 2, right? So 2 nines are 1. Okay. So accordingly, so you have to compute it. 2 fours are carry is 1. 2 twos are 4, 0. 2 ones are 0. 1 0 0 1 1. That is the output you are getting for 18. 1 0 0 1 1. Meaning what here? 0 0 1 1 is the sum and 1 was the Cout. Okay, so this is same way doing addition like this. 1 0 0 1. 9 means 1 0 0 1. No, so 1 0 0 1. You do the addition, what you will get here? See, just so 1 1 0 1. So you'll get 1. Okay, so then 0 0 0. Then 1 1 0. So something I have made mistake, I think, right? So here it was 0, right? So it is wrong. So it is coming correct now. So 0 0 1 0 was the answer and 1 was the Cout. Similar way you do the remaining. So A is 10, B is 15. Okay, so 10 is 1 0 1 0, B is 1 1 1 1, 15, right? So far scene was 0. So next case what I will do, scene also I will take as 1. Okay, and now we have to consider scene also in the computation. So far we are not considering. So A is 10, B is 5. So 10 plus 5, 15 plus 1, 16. Okay, so like that you have to consider. So this is how we give the simulus to the, so few combinations. You can change the combinations and also you can try. Okay. So it will be lengthy, right? If you write all combinations. So just if you see few and if it is giving addition correctly. Okay. So then end this because initial begin we have made, and finally the end of the module. Okay, so with this we have written the stimulus module for 4-bit triple carry full adder. So now whatever combinations we have used this, so just we'll see the simulation output, how the monitor statement will display. Okay, so monitor we have written no same way. First in simulation time will come, then ABC in, and then Cout and sum will come. Okay, the same pattern, so that will display here. See here, initially simulation time. Okay, so it is 0, and then 0 0. First A and B 0 0 we have taken, C in also 0. So sum is 0 0, Cout is 0. Next 5 simulation time units we have given delay. Okay, assume it is. So we have given next 3 and 4 as the input. So C in is 0. So Cout was 0 and it was 7. I told you, right? So just verify that. Next we have taken 2 and 5 combination. So 7 is output, 0 is the output. Okay, so since I can write it in single line, okay, normally it will come in single line, but it is PPT, I have taken it in next line. Okay, so just to represent nicely. So after this only it will come, this dash dash line, it will come, and Cout and sum will be displayed like this. Okay, so understand like that. Then A we have taken 10 and B have taken 15 and C in is 0. Okay, before that we have taken this 9 9, right? 18, I told you, right? Cout is 1 and 0 0 1 was the. Okay, so then when you do this addition, you got sum is 1 0 0 1 and Cout is 1. So next case what we have done, scene also we have taken 1 here, and along with we have taken 5 and 10 15. So 16 means sum is all 0 and the carry out will be 1. Okay, so this is the simulation output of the 4-bit triple carry full adder. So with this you have understood what is meant by gate level modeling. So the gate and or gate types, buff not gate types, how we used it, and also we have used how we have used the user defined and how we give instance names, how to write a program from starting from IO diagram. Anywhere I have by heart concept is there here? No, right? So yesterday's multiplexer as well as today started with IO diagram. From that truth table, from that design, first let us dig on the design, and then we started one-to-one correspondence with Verilog. Okay, so this is a very simple way. I hope you have liked this. Okay, so with this we'll end the video here. In the next we will be continuing with some delay concept with respect to gate. Okay, and then again we'll have the examples and exercises. Okay, thank you.